Alright, so this is the 7th video in the series of name reactions, and today we are going to discuss about Azide-Alkyne Cycloaddition. You can also call it as click reaction. So here's a question for you. This is my starting material and I'm reacting this with sodium azide in presence of DMF as a solvent, and we are getting molecule A. Now this molecule A further reacts with this alkyne in presence of copper iodide at room temperature for 10 minutes and we are getting B. So I want you to find out the structure of A and B. So before solving this question, first let's understand what is azide-alkyne cycloaddition, that is a click reaction, and the mechanism of it. Okay, so as name suggests, we have azide-alkyne cycloaddition. So one of the reactant will be azide and the other reactant will be alkyne. So let me take the simplest alkyne possible, that is acetylene. These reactions are usually done in presence of heat and you need metal like copper. And you will be able to form a product that is nothing but triazole. So let's see the mechanism and find out the product. So this Rn3 can be written as, so overall it's a linear molecule and a neutral molecule because we have a cation and anion sitting on the same molecule. So this N3 part of the molecule is a linear. And we also know that alkynes are also linear. So let me bring my alkyne. So this is my alkyne. Now mechanistically, this nitrogen with its lone pair will attack at this carbon. One of the bond out of these three bonds will be used to attack at this nitrogen, and this nitrogen will get neutralized. So it's more like the arrow pushing mechanism, and you are going to form. So let me number them. This is 1, 2, 3. 3 is getting attached to 4, and this is my 5. So the product will look like so let's say this is my 1. 1 is bonded to carbon number 2 which has hydrogen. 2 is doubly bonded to 3 which has 1 hydrogen. 3 is singly bonded to this nitrogen 4th which has this R group also. Now this nitrogen is singly bonded to nitrogen number 5 and nitrogen number 5 is doubly bonded to nitrogen number 1. So this is the product of alkyne azide cycloaddition, where it's more like the arrow pushing mechanism and you make this triazole moiety where 3 nitrogens are present in a ring system. So now let's go ahead and solve some problems based on this azide-alkyne cycloaddition. Okay, so here's the first question. I'm reacting this particular azide with this terminal alkyne in presence of a organometallic reagent, and we are heating it up. So pause the video, try the mechanism and find out the mixture of product formed in this reaction. Okay, so let's begin. So I can write this ArN3 like this one, and we have a terminal alkyne, so I can bring my terminal alkyne here. Now at this point of time, all we have to do is we have just seen the arrow pushing mechanism. This nitrogen with its lone pair will attack at this carbon. This bond will migrate at nitrogen and this bond will get neutralized. Will help the nitrogen to get neutralized. So the product here will be, so this is my 1, 2, 3, 4 and 5. So the product will be, first you form a triazole ring. Okay, this is my nitrogen number 1 bonded to carbon number 2 which has this methyl group, which is doubly bonded to carbon number 3 which has a hydrogen. 3 is bonded to nitrogen number 4 which has a AR group. 4 is singly bonded to nitrogen number 5 and nitrogen number 5 is doubly bonded to nitrogen number 1. So this is the product for this reaction. But here's a twist. So this is my azide. Now alkyne is a linear molecule. It can do 180-degree flip, and this alkyne can approach this azide in this way also, right? So alkyne did 180-degree flip, and now methyl, which was at right side, is now at left side. Okay, so if we go by this mechanism, this nitrogen attacks here, this will attack here, this will get neutralized, and this will give me, so 1, 2, 3, 4 and 5. So this is nitrogen number 1, carbon number 2, carbon number 3 contains methyl, nitrogen number 4 has this AR group, this is nitrogen number 5. So this is the product. This is the another product possible. So all we did is we simply flipped our alkyne to 180 degree, and this methyl, which was at right side, is now left side. So this is the another way by which the alkyne can approach this azide, simply because the alkyne is a linear molecule. So these are the two products possible for this reaction. But what do you think? Which one is going to be the major one? This one or this one? What do you think? So if you look at this product, we have aryl group and a methyl group coming close to each other and causing the hindrance to the overall system. But here, the AR group and the methyl group are far from each other. That's why giving the stability to the molecule. So hindrance is the reason why this molecule is the minor product, whereas this one, where two R groups are sitting far from each other, is the major product. So always remember, when you are doing the click reaction or the azide-alkyne cycloaddition, you need to keep two R group far from each other. Okay, so here's the another question. So I have this terminal alkyne, I have this azide, and I have one more alkyne. And we are reacting this with copper chloride, and we have potassium tert-butoxide as a base. So pause the video, draw the mechanism and find out the product. Okay, so let's begin. So we have a terminal alkyne and we have a base. So let's go ahead and grab this proton. Okay, so this is my terminal alkyne and we have a base, that is potassium tert-butoxide, that can be written as this one. So this oxygen with its lone pair will grab this proton and will generate this carb anion at the alkyne carbon. So we have a alkyne with a carb anion. Now the second alkyne will come. Okay, so we have a carb anion, we have a carbon bromine bond. So substitution is going to happen. This carbon anion will attack at this alkyne carbon and this CBr bond is going to break. And you will generate. So this alkyne carbon is now connected to this alkyne carbon, which is further attached to R double dash. So this is the intermediate. Okay, we have generated two alkyne in a single molecule. Now furthermore, we have an azide. Just because we do not have any idea about what are this R and R dash, we can simply go ahead and form a triazole ring at any of this alkyne by using this azide. Okay, so we have just formed this one, and now we are going to react it with the azide in presence of copper chloride. So now we have used the potassium tert oxide. Now it's time to use the copper chloride and do the click reaction. So this is my azide. Let's use this alkyne. So this nitrogen with its lone pair will attack at this carbon. This bond will migrate to nitrogen and this bond will be used to stabilize the nitrogen atom. So this is 1, 2, 3, 4 and 5. So the product will be, so we are going to simply generate a triazole ring. So this nitrogen is 1, which is attached to carbon number 2, which has this whole group. Okay, 2 is doubly bonded to 3, which has this R group. 3 is bonded to nitrogen number 4, which has R1. And 4 is singly bonded to nitrogen number 5, which is doubly bonded to nitrogen number 1. So this is the product for this particular reaction. Okay, so here's another question. We have this azide and this particular alkyne, and here we are using copper acetate. So pause the video, try the mechanism and find out the product. So I can write this ArN3 like this one. Now this alkyne can approach my azide in this way, and it can also approach the azide so 180-degree flip. CO2Me, which was at right side, now I'm going to write in the left side. So this is the another way by which alkyne can approach the azide group. So let's write the product from both the case and find out the major product. So this nitrogen with its lone pair will attack here. This will attack nitrogen and this will get neutralized. So here we are forming 1, 2, 3, 4, 5. Whenever you get confused, just number them and things will be all right. So nitrogen number 1, carbon number 2 having CO2Me, carbon number 3 hydrogen, nitrogen number 4 Ar group and nitrogen number 5. So this is one of the product. And the other product can be, so this nitrogen attacks here, this attacks here and this get neutralized. So 1, 2, 3, 4 and 5. So we have here nitrogen number 1, carbon number 2 having hydrogen, 2 is doubly bonded to 3 which has CO2Me, a ester functional group, nitrogen number 4 having Ar, and nitrogen number 5 is doubly bonded to nitrogen number 1. So this is the another product possible. And now you know which one is going to be the major product. The major product will be this one, simply because the Ar group and the CO2Me are far from each other. So that's all you have to look at. This one is going to be the minor one simply because Ar and CO2Me are close to each other and causing the hindrance to the system. That's why this is the minor and this one is the major product where two R groups are sitting far from each other. Okay, so here's the another question. This time I have a kind of haloalkane and we have this terminal alkyne and we are reacting this with this palladium complex, copper iodide and DiPeA, and by using this we are getting A. Now this A in presence of TBAF and water giving me B. So another example of azide-alkyne cycloaddition. So pause the video, try the mechanism and find out the structure of A and B. You have to think about the major product of A and then move forward to the product B. Okay, so let's begin. I think I'm missing something. We also need a azide, right? So here I am giving you azide. Let me use the HN3. Okay, so another reagent in this arrow is HN3. So let's begin. So DIPEA is a base. The structure of DIPEA is diisopropyl ethyl amine. So we have amine, diisopropyl and ethyl. So diisopropyl ethyl amine. So this is what we call the DIPEA, which is simply a base. So base is going to grab the proton. In this molecule, we do not have any acidic proton, but this terminal alkyne do have a acidic proton. So let's go ahead and grab this terminal proton. So this is my proton. So this base will grab this proton and will generate carbon ion at this alkyne center. I can write this SiMe3 like TMS, that is trimethylsilane. So we have a carb anion. We have a carb anion and we have this ARI group. So this will attack at this AR group. Iodine is going to leave and you have done a substitution. And this is the product for A reaction. I mean the product we are looking for A. Okay. So now we have found out the A. Now let's go ahead and draw the structure of P by doing azide-alkyne cycloaddition or the click reaction. So A was simple. All you did is by using this base, you grabbed this proton and did the substitution reaction and formed the A structure. Okay, so this was the structure of A. And now we are reacting it with HN3. And in later part, we are also using TBAF. And we have to find out the product. So HN3 can be written as so this is plus, this is minus, and this is my alkyne. So let's do the arrow pushing mechanism. This will attack here, this will migrate here, and this will get neutralized. So we form 1, 2, 3, 4, and 5. So this is 1, 2 has AR, 3 has this TMS group, this nitrogen contains hydrogen, 4, this is 5. So this is one of the product. Now this alkyne can also do 180-degree flip, and this can also give me so this nitrogen attacks here, this migrates here, and this get neutralized. 1, 2, 3, 4, and 5. This time TMS will be here and AR will be here because we did 180-degree flip. So this is the another product possible. In this case, both the product can be 50-50 because we have no sort of comparison because this nitrogen simply contains the hydrogen group. So it's possible that both of them forming 50-50%. Okay, we also have a TBAF, and TBAF is known to do deprotection of silyl functional group. So all we have to do is just simply remove the TMS group because we have a TBAF. You can watch my video on deprotection for alcohol functional group, where we discussed TBAF in detail and where I showed the mechanism that how this TBAF is deprotecting TMS. So whenever you see TBAF, you have to remove your TMS group, that is trimethylsilane. So the final product will be this is the one product, and this is the another product. So these two are the final product. Okay, so I hope I'm clear. In first step, we form this alkyne by substitution. Now this alkyne can approach this azide in two different forms, giving me these two products. And we have a TBAF, so we are simply going to deprotect TMS and we'll keep hydrogen there. So this is the two product of this reaction. Okay, here is the another question. So this is a terminal alkyne. This is my azide. I'm reacting this in presence of copper sulfate and heating this reaction for 1 hour. So what is the product? So feel free to pause the video, try the mechanism and find the product. So this is a pretty straightforward. This N3 part of this azide is a linear one. Let me go ahead and draw my linear azide. Okay. So this is my EtCH2N3, EtCH2N3. This one is plus and this one is minus. Now I have this alkyne. So this is one of the way I can write this. The another possible way is you do 180-degree flip to your alkyne. So this hydrogen, which was at right, is now at left and approaching my azide functional group. So this nitrogen attack here, this migrates here, and this get neutralized. So this will give me 1, 2, 3, 4, and 5. So we have a triazole ring. This one is bonded to 2, which has hydrogen, which is doubly bonded to 3, which has this pH group. This nitrogen contains CH2ET. This nitrogen is singly bonded to nitrogen number 5, which is doubly bonded to nitrogen number 1. So this is one of the product. The another product can be, so this nitrogen attacks here, this migrates here, and this get neutralized. So 1, 2, 3, 4, and 5. So we are going to generate once again the triazole ring. This is 1, this carbon is 2, contains pH. This carbon 3 contains hydrogen. 3 is bonded to 4, which has this CH2ET group. And this is nitrogen number 5, doubly bonded to nitrogen number 1. So this is the another product. What do you think? Which one is going to be the major one? So this one is the major, because we have two alkyl groups sitting far from each other, doing no hindrance to the system. But look here, these two groups coming closer to each other, causing hindrance to the system, and this is the minor product. So that's it for today. We discussed azide-alkyne cycloaddition. You can also call this reaction click reaction. Okay, this is the mechanism, a arrow pushing mechanism. Just number them, form a triazole ring. These reactions are usually done in presence of metals, and you can also distinguish between major and minor product. Major will be two R group far from each other. Minor will be two groups coming close to each other, causing the hindrance. So that's it, and thank you for watching. If you like the content, please share and subscribe.